Hello everyone, George here, and welcome back to a one-day game crash course specifically designed for teachers in New Jersey who are attending my one-day lecture on how you can utilize games and programming to excite students into STEM or STEAM or whatever you want to call it. So that being said, we need to cover some fundamentals before we continue. Now at this point, I'm assuming you've already taken a little bit of time and you've downloaded your preferred game engine as well as your preferred 3D modeling package. Now I'm going to be utilizing the Unity engine as you see here. The Unity engine is completely free. If you look up Unity 3D on your preferred browser as well as your preferred search engine, it should be one of the first things that pops up. Go ahead and install it and you'll be looking at something similar to what I have here, although the layout might be a little bit different. This is the default layout, and of course I've gone and created my own separate layout for this. And we'll be jumping back and forth into this view just so I can show you different things. I'm not going to spend the time to talk about every little button and piece on the interface. Instead, as we learn things and come up with things, I'm going to jump over into the appropriate program and show you what I mean. And the second thing you're going to need is your 3D modeling package. Now in this case, I'm using Autodesk Maya LT 2017, which I have a subscription to every month for about $30, $35. If you're trying to look for something free, there are other options such as Blender, SketchUp, and so forth that are available, and I recommend you go with the one you want. However, if you would like to follow along, you will be needing Autodesk Maya. That being said, there are free versions, education versions of this software. I would recommend checking them out before you feel like you need to pay any money. Now that being said, why don't we jump on into the lecture material and get a sense of what's going on here. So first of all, bam, there we are. Fundamentals. So this, for some of you, might be incredibly simple, and for others, this might be the first time you've ever seen something like this. And the idea here is that our graphical system consists of the following elements. We have things like input devices, mice, keyboard, our tablet interface with touch commands and so forth. We have the actual processor, or our CPU, and then of course our processor executes code, which is our application, which is what we are going to create using these programs, and then our information is stored in memory. And there's sort of this whole cycle that goes around with our processor. Now, I drew a vertical line that's black between the processor and the graphics processor because the processor and graphics processor are two separate entities. The processor is doing a lot of work, a lot of CPU intensive work. It could be dealing with sound, it could be dealing with physics and a bunch of other things, or just the state of your operating system. Whereas the graphics processor is all about, at blazingly fast speeds, as fast as possible, it is trying to output information to your screen. The communication between the processor and the graphics processor is relatively slow. And one of the things we're going to learn as this series goes on is we want to optimize this talking back and forth as much as possible to reduce, well, low frame rates, or that is really bad stuttering of what we see on the screen. So that's something you need to think about. And then of course our graphics processor pushes out a frame buffer. A frame buffer is nothing more than all the pixels you see on the screen. It's what we're looking at right now. If you were to consider your frame buffer, you're looking at some sort of a display, and that display has a frame buffer, and that frame buffer is continually updating based upon what you're doing. Now for the most part, nearly all graphics output pixel information. And if you think about it, you already know about this. Remember how we all want to jump from SD to HD, and now we're into 4K and 8K displays? Well, what are we doing? We're increasing the number of pixel information on the screen. This rasterization step, the conversion of shapes to pixels, is an interesting one, and it's something that's very important within computer graphics. But basically, pixel elements, or pixels, are stored in memory in that frame buffer I'd mentioned before. And our resolution is determined by the number of pixels we have in the width and that is the vertical and horizontal areas. And then finally, we also have another, or a third dimension if you want to think about it, called the depth. And the depth is the number of possible values each of those pixels can actually have. So if we take a look here at this eyeball zoomed in, we can see that our depth is actually enough to compensate for having a red color, a green color, and a blue color. Now if our depth was 1, we would only be able to have two colors. That is 0 and 1, on or off. So you'd either see black or you'd see white. With 8 bits, we get up to 256 colors. With 24 bits, or I should mean, by 24 I mean red gets 8, green gets 8, and blue gets 8, we get 16 million, almost 17 million colors really. And then we got to think about, well, what if we want transparencies? What if we want overlays? What if we want one screen to fade into another? Well, what do? We add another 8 bits and we get 32 bits. And that gives us plenty of possible values so that we can blend things and make things look pretty nice. Now the big question is, how do we get from a 3D world to a flat 2D monitor? If we bring over Maya really quick, and I just throw down, so up here under my shelf, this area right here is called the shelf, under polygons, I can throw down a cube. And that looks pretty 3D to us. In fact, if I right click and go to Vertex Mode, you'll notice it's got these different points, and those points are expressed in 3-dimensional coordinates. And I can move them around and put them wherever I want to, basically. But the idea is that this, as far as Maya is concerned, internally is a 3-dimensional shape. But how does this 3D shape get converted over to a 2D object? More importantly, how does that 2D object look right? I'm spinning around this object right now. There's some sort of a virtual camera going on, and that camera is looking at this cube, and my computer is interpreting where this camera is based upon how I rotate about it, and how this cube should look on the screen. That's actually a complicated thing to do if you think about it. So how do we go from that 3D world represented in the computer to a flat 2D monitor, which is what we're actually seeing with our eyes on the display? Well, the first step actually is to accurately describe our world. And the way we do that is through primitive types. By primitive types, I mean a mathematical way of describing all of the different points or lines or line strips or line loops or quads or polygons and so forth and so on in our environment that makes everything up. The reality is everything we deal with are pretty much triangles. When we take a look at our object, like our, this one right over here, this object right here can really be decomposed into what? It can be decomposed into triangles. It's completely actually composed of triangles or quads. So I click on this object and I go to Mesh and I hit Triangulate. Here you are. So here's all the different triangles that our object is actually made out of. And those are the polygons. And that's why polygons are so important, because all of our objects are ultimately made out of them in computer graphics. Why don't we take a look at a more complicated scene really quick, just in case you're not believing me, that truly really complicated things can be made out of something as simple as triangles. So let's jump into a project I'm working on right now. Here's a test layout for a horror game, and we can take a look, and things look all right. Let me hide a few things. So I'm hitting Control H as I'm selecting different objects. I'm selecting the roof and the floor and so forth. But if you take a look, we've got all these different objects in here. We've got a curtain, we've got a bathtub, we've got a toilet and so forth. And maybe here and there you can kind of see some of the polygons, but as soon as I click on an object, you should notice that it's composed of these different, well, it's got this wireframe, as we call it, over the entire area. And this wireframe is showing us how it's broken down. And if I go ahead and grab one of these objects and I go to Mesh and I hit Triangulate, now you can see all the different triangles that compose that object. So hopefully you now believe me. All these different computer programs you look at, all these different computer graphics you're dealing with, it's basically just lots and lots of triangles being processed by your computer as fast as possible to give you something interesting to look at. And here's another example showing you a caterpillar I created. Here this caterpillar is composed of thousands of individual points detailing exactly how it should look. The more points you have, obviously, the closer an approximation you're going to get to what that thing should look like, as you can see here. So really, you're in a battle between realism versus how many points you have. Because if you think about it, the more points you have, the more complicated it is, and the more time it takes your computer to figure out what's going on. However, too few points, and it looks bad, and the person playing the game is going to say, well, those look horrible, the graphics are junk. Another thing we deal with typically is local coordinates. So we deal with different coordinate systems. So if you think about yourself and where you're sitting right now, you have your own local coordinate system. For you, you have a forward direction, which is pretty much usually where your head is facing. So you're probably facing some sort of a tablet or monitor or some other device, maybe a cell phone, and that's your forward direction. And then you have your left and your right directions, okay? And when we create different objects in our 3D worlds, we typically create them in a way that makes the most sense. Now I'm using the picture of a Zergling from Blizzard Entertainment's StarCraft game to give you an idea of what I'm talking about. But the idea here is that forward is the direction it's facing. To its right is the x-axis and up is the green or y-axis. We do call this local model or object space, and that's where all of our models are normally kept. Now, each model itself gets its own local coordinate system, and it is then described in world coordinates when we put them all together in a single space. And what happens there? Well, if you take a look here, each of those little models there, each of those zerglings, are coming to fight this big old guy over there, this ultralisk. And you'll notice each of them have their own forward direction. They have their own idea of what forward means. And this is going to become important later on as we dive into coding our characters and making sure they move in the right direction. Because if you think about it, while they all exist in one common world, how they want to move is not based on the world coordinates. It is instead based upon their local frame of reference. What direction is forward to them? And that's something we need to take in consideration. So we'll be doing that with that shortly when we jump into Unity, probably in the next video. For the most part, every object we deal with is just going to have translate, rotate, and scale. And if you're a little bit flaky on what those means, here you go. We can translate, we can go up and down, we can rotate as you see there, and we can scale. How can I teach you that this is really all there is to things? Well, if you're using Maya, the W, E, and R hotkeys on your keyboard are pretty much just that. W is equal to translate, E is equal to rotate, and R is equal to scale. And you can see this little object in the center, which is called a gizmo, changes appropriately. When I hit the W key, I can move this object around. If I hit the E key, I can rotate it. And of course, if I hit the R key, I can scale it. Let's go back. There we are. And then even in Unity, if we jump on over here, let's go to Create a Game Object and go to 3D Object, and I'll create a basic cube. I'll hit the F key to frame up. If I hit W, we'll notice we can move it. If I hit the E key, we can rotate it. And then the R key allows us to scale it. And over here, in our inspector, which whenever we select an object will be populated, you'll notice right at the top is this thing called a transform. And the transform is basically the distillation of our position, rotation, and scale into one location. And here we can go in and actually, if we click on this gear, hit reset. And now everything's back to 0, 0, 0, except for that position. Let's fix that. There we are. And as you can see here, the translation, rotation, and scale is incredibly important. And if we take a look as well, if I hit the W key, there's this local coordinate. If I rotate the object, watch what happens. That Z-axis, that forward axis, rotates with it. And that becomes that object's forward movement. So, you want to get a little scared, you want to mess with your students a bit. Well, the reality is everything is handled by linear algebra. And I'm showing you briefly some of that linear algebra, where right here we have different matrices. This matrix right here is our translate matrix, where the tx, ty, and tz represent their location in space. We have our scale matrix right here, which allows the object to be scaled up or scaled down. And then finally, on the end, we have our rotation matrices for the x-axis, y-axis, and z-axis. Now, another thing to understand is the fact that we're dealing with a camera. So all of our objects are in one world, as we can see here in this kitchen. But they're also spaced and located based upon this camera that I'm rotating around. So if I go to View, Select Camera, we can see that as I'm moving, these camera locations are updating, and we're getting a different view of the scene based upon where that camera actually is. And that's important to understand. There are steps with how we create an image. We go from local coordinates to world coordinates to camera coordinates. And if you move that camera around, you're going to get a different image each time. That, of course, means more processing. Here you can get a sense of what's going on. So here we have our camera. It's located somewhere in our world. But what ends up happening in this process is that we take the camera and we actually invert where it is, or negate it, I should say, so that it is looking down the negative z-axis or down the positive z-axis. It depends which system you want to use. But either way, we move the camera to the origin. By doing so, what happens is that all the objects also get moved in the scene. The reason why we move it to the origin is simply convenience. By doing this and rotating all the objects in the world, it just means that our camera is at 0, 0, which just makes things a little bit easier for us. Here we have the frustum, which looks like a truncated pyramid. What do I mean by truncated? Well, basically there's a beginning and an end to it, and this is called our near and our far clipping plane right here. Anything closer than this won't be rendered. Anything further than this will not be rendered either. Only objects within this area will actually be rendered and displayed. Now finally, this is a description of all the different transformations we have to go through to get a picture on the screen. Now I'm not expecting you to understand all of these right now, but you should at least understand the top portion, which we've kind of covered. We go from model space, which is where we created that model, has its own reference with its own Z forward and its own left and its own up. Then we go to world space, which is how every object in the world is oriented with respect to one another. We put a camera in there and move it around to some location. And then of course the camera we end up putting at the origin, and then we rotate everyone and move everyone opposite to make that thing back at the center. Then finally we need to do some other steps, such as making all the lighting work so it looks proper, projecting this onto an image, clipping anything that isn't actually there, and then of course mapping it to your screen, because everyone has a different size screen, whether it's 4x3, 16:9, and so forth. Now this has only defined the shape of the object and has absolutely done nothing to define the visual properties or the surface of that object. If you had no light in the scene, you'd end up with this flat shaded object or caterpillar we see right here. To describe how this object should look, we really need a material, which is a complete description of the visual properties of that object. Here we have an example of multiple materials being used to describe all the different portions of this building, whether it's brick, glass, or metallic, or water, or vegetation on the sides. Really, a material is just a container holding the algorithm used to render it, all the different images it might need, as well as different parameters that you get to set to tell it exactly how to work. Here is a different program called 3D Studio Max. This is using its material or map browser to show you how a material might be set up. Now if you're in Maya instead, you'll be using Window and go under Material Texture Baking Editors in the Hypershade. Now within the Hypershade, we have these different materials called Lambert and so forth, and if we click on one of them, and then hit this button right here, which is Input and Output Connections, you'll notice we have this thing called our Lambert material. And it can take in different things like colors and ambient colors and so forth, and define how an object should actually look. But we'll get more into that later on. Now once we have textures and lighting, we can go from this over here to this caterpillar on the side. Now, in order to get all those interesting colors, it actually requires us to do something called unwrapping, or taking this three-dimensional object and flattening it down into two-dimensional space, which is what you see over here on the side. Not only do you get to code your own stuff and make it happen, but you also can code how the material behaves, and more importantly, the shader as it's called, which describes exactly how to process the vertices and the pixels on an object. This is a shader I wrote a long time ago for the program WorldVisWizard, which we're not using right now, but it's fine. It's another 3D engine. And the idea here is it's a Bioshock representation of if you took this brick area and applied a special material and a special shader to it over here on the side, it'll transform that simple color thing into this grayscale image over here with noise, as well as this undulating effect down at the bottom. So it's kind of cool. All right, so we've gone over all of that, but we've got one thing left to talk about, and that's lighting. And that's the key to making a scene look really, really nice. Lighting is determined based on normal rendering equations, and things have gotten much more complicated over the past 5 to 10 years with how we deal with handling lighting. And a lot of the improvement we have in video games has been due to the fact that our lighting algorithms are getting better and better. Now we have local illumination models. Local means we look at a light source, we look at where an object is, and we ignore everything else in the scene, and we just see how it interacts with that object. Global illumination is where we deal with how the light bounces around the scene, what it might hit, how it gets to where it should be before reaching a virtual camera. Now, simplified local illumination has to do with 3 terms, and this is sort of the old school way of doing things, but if you're working on a cell phone or a tablet, it's still very popular, and it's used a lot because it's simple, quick, and it gets the job done, and it doesn't look that bad, really. Ambient is sort of the global illumination in a world. That is, how much general light is there. Instead of a world being completely pitch black, if you notice that it always seems to be a little bit lit up, you'd want your ambient value to be something other than 0. Diffuse is how much light is reflected off the surface It's a very simple parameter, but when a light source hits the surface, how much light bounces in all directions. So this has nothing to do with a highlight. It has nothing to do with what's called the specular highlight, which is a reflection of the light off the surface. But instead, the light sort of hits the surface and is bounced in all different directions, and it lightly illuminates the entire thing. So if we look at these circles down here, we'll notice that the backside is lit up somewhat. It's a darker color, but it is a brown color, not a complete black color. So that's the ambient component. And then if we come around to the side, we'll notice that as we go from this backside to the front side, the diffuse area gets brighter and brighter and brighter until we get this sort of gold color. And then finally, we have this highlight in the center, and that's our specular highlight, which is sort of falsifying the reflection of light off of its surface. All right, and that's it for part 1 of our fundamentals section for a one-day game crash course. Remember, if you enjoy this series, give me a like. If you dislike it, give me a dislike and a comment as to why, so I can improve. Thank you very much for watching, and tune in for section 2 next time.